Welcome to this lecture on first-order partial differential equations. Imagine you are hiking on a large, uneven mountain. Your current elevation depends on two separate coordinates, your position moving north to south and your position moving east to west. If you want to know how steep the ground is, you cannot just ask for the slope because the steepness changes depending on which direction you step. You need to know the rate of change in both directions simultaneously. This is exactly what we will learn to model today. Now that we have our mountain analogy, let us define this mathematically. A partial differential equation contains an unknown function of two or more independent variables, along with its partial derivatives. An independent variable is an input you can freely change, like space or time. The dependent variable is the output you want to find, like temperature or elevation. A partial derivative measures how the output changes when you vary just one input, keeping all others completely frozen. When we say first order, we mean it only contains first derivatives, representing the immediate direct slope, without any second derivatives for curvature. This brings us to the mathematical representation. The general formula ties all these pieces together. The capital F stands for some mathematical relationship that equals 0. Inside, x and y represent our independent variables, which could be coordinates in physical space. The symbol u represents the unknown function we want to find. The partial derivative of u with respect to x shows how the function changes as we move strictly along the x direction. Similarly, the partial derivative with respect to y shows the rate of change strictly along the y direction. If the rate of change increases, the slope in that specific direction becomes steeper. Let us visualize what these partial derivatives actually look like on a graph. Here you are seeing a three-dimensional surface, which represents our unknown function u depending on x and y. Look at point P on the surface. The two arrows extending from it are the tangent vectors. One arrow points strictly along the x direction, representing the partial derivative with respect to x. The other points strictly along the y direction, representing the partial derivative with respect to y. This diagram shows exactly how a first-order equation captures the slopes in different directions at a single point. Now that we can visualize the slopes, let us look at how these equations are actually constructed. One of the best ways to understand where partial differential equations come from is to build one from scratch. We do this by eliminating an arbitrary function. An arbitrary function is just a general, unspecified rule that relates variables together without giving a specific formula. To see this in action, let us imagine a wave moving across a string, where the shape of the wave stays exactly the same as it travels forward in time. We can describe this wave's height using a function of position and time. This concept leads us to the mathematical model of our wave. Here, u is the height of the wave, and f is an arbitrary function representing the initial shape of the wave. The variable x is the position, t is the time, and c is the constant speed at which the wave travels, measured in meters per second. The expression x minus c times t ensures that as time moves forward, the shape shifts to the right at speed c. If the speed c increases, the wave covers more distance in the same amount of time. To turn this into a differential equation, we need to find its partial derivatives. Let us take those partial derivatives to set up our equation. First, we take the partial derivative of the wave height with respect to position x. Using the chain rule, we take the derivative of the outside function f, giving us f prime, and multiply by the derivative of the inside argument with respect to x, which is just 1. Next, we find the partial derivative with respect to time t. Again applying the chain rule, we get f prime, but this time we multiply by the derivative of the inside argument with respect to t. Since x is treated as a frozen constant, the derivative is negative c. Continuing from our derivatives, we now have two separate equations that both contain the same unknown term, f prime. We can eliminate this arbitrary function entirely by substituting the first result into the second result. This is a crucial step because it transitions our specific wave model into a general differential equation. By rearranging the terms to the left side, we get a clean linear relationship. This gives the final result, known as the one-dimensional transport equation. It tells us that the rate at which the wave height changes over time is directly proportional to how steep the wave is in space. So, we have proven how to construct a partial differential equation. This brings us to how we actually solve them. Let us start with a very basic method called direct integration. Sometimes you will encounter an equation that only involves a derivative with respect to one variable, even though the unknown function depends on two variables. We can solve this using a method similar to basic calculus. We simply reverse the process by integrating both sides with respect to that one variable. The trick is that during this integration, we must treat the other variable as if it were a fixed, unchanging number. Let us look at the specific equation we want to solve. This equation states that the partial derivative of u with respect to x is equal to 6x squared plus 2y. Conceptually, this means we know exactly how the function slopes in the x direction at any given point. Because the derivative is only taken with respect to x, we can reverse the process. If the value of y increases, it simply shifts the slope by a constant amount for any given x. We will now integrate this expression to recover the original unknown function u. Let us solve this step by step. We are given the partial derivative with respect to x, so we set up the integral of the right side with respect to x. We integrate each term separately. The integral of 6x squared uses the standard power rule, giving us 2x cubed. For the second term, 2y is treated as a constant multiplier for x, so it integrates to 2xy. Finally, instead of a normal constant c, we must add an arbitrary function of y, written as g of y. This is because any function depending purely on y would disappear when taking a partial derivative with respect to x. Now that we have used direct integration, let us tackle a slightly more complex scenario, where derivatives for both variables appear in the equation. To solve this, we use a powerful technique called the method of characteristics. This method works by finding special geometric curves in the coordinate plane. Along these specific paths, the complex partial differential equation simplifies into a basic ordinary differential equation. You can think of these characteristic curves as the natural paths along which information flows in the system. If we can track these paths, we can easily find the solution to the entire equation. Here is the formula we will solve using this new method. In this problem, we need to find a function u, where 2 times its slope in the x direction plus 3 times its slope in the y direction always equals 0. The method of characteristics tells us to look directly at the coefficients in front of the partial derivatives. These numbers, 2 and 3, are not just random constants. They dictate the exact direction of the characteristic curves in the xy plane. If these coefficients were larger, the flow of information would shift to a steeper angle across the plane. Let us set up the solution by finding those characteristic curves. We write the coefficients as a system of simple fractions, stating that for every 2 units we move in the x direction, we must move 3 units in the y direction. To solve this, we cross-multiply to get the differentials on opposite sides of the equal sign. This separates the variables, making it possible to use standard calculus techniques. Now, we integrate both sides to find the algebraic relationship between x and y along these special geometric paths. Continuing from our integration, we get 3x equals 2y plus an arbitrary constant c. We can rearrange this equation to isolate the constant c on one side, giving us c equals 3x minus 2y. This constant represents a specific characteristic line in the plane. The theory states that the solution u must be constant along these curves as well. Therefore, the unknown function can be any arbitrary function of this constant expression. This gives us our final answer, meaning the value of the function only depends on which characteristic line you are standing on. Before we finish, let us understand why these equations matter in the real world. First-order partial differential equations are incredibly important because they are the fundamental language of transport and conservation. Whenever a physical quantity moves from one place to another without instantly spreading out, a first-order equation is used to model it. Without these equations, engineers could not predict how traffic jams propagate backward down a highway, and meteorologists could not model how sharp weather fronts sweep across the globe. They provide the mathematical foundation for understanding how shapes and concentrations shift through space over time. Let us summarize the key takeaways from this topic. We learned that a first-order partial differential equation relates an unknown multivariable function to its immediate rates of change. We saw how to construct these equations by eliminating arbitrary functions from known wave models. We also explored two ways to solve them, using direct integration when only one derivative is involved and using the method of characteristics to find the natural geometric paths of the system. By mastering these equations, you now have the mathematical tools to describe and predict the flow of physical quantities in our dynamic world.